Okay, so let's take the family of 5 periodics as usual in the elliptic billiard. It could be n equals 5 here, but it could be anything. And I want to show you guys, recall before we start this, that this family has a constant perimeter L shown up here. In this case, the axes are semi-axes are 1.5 and 1. This is showing the semi-axis of the caustic. This brown thing here, the confocal caustic. But recall that this family conserves perimeter. It also conserves a quantity known as Joachim-Stall's constant, J, but it also conserves the sum of cosines. Its area is variable. Alright, now in this video I'm going to talk about petals, bicentric families, and inversions. So let's start off by considering the petal family to these n periodics with respect to F1. So let's draw them here. So here's a petal polygon, this orange thing, whose vertices lie at the feet of perpendiculars drop from F1 onto the sidelines of my n periodic. So I get this family here. Let's animate this to look at this family. Okay, so it's this family of orange polygons. Now the cool thing about this family is that it is automagically bicentric. That is to say that thanks to a special combination of geometry properties of the confocal pair, if you take the petal polygon with respect to F1, you get a new family which is bicentric. Okay, and it's going to be inscribed in a circle, this dashed orange circle, whose radius is equal to the major axis of the caustic. So you can see that the circle is tangent to the caustic at its right and left vertices. Okay, so let's watch this some more. Now I can report up here the perimeter of this family, its area, and also the sum of cosines. So you're going to notice that this family has variable perimeter, variable area. However, like its parent 5 periodic, it also conserves the sum of cosines. Very well. Now let's repeat this operation. I now want to compute the petal to this petal family, the so-called square petal family. So let's draw perpendiculars from F1 onto the sidelines of the orange family and mark off the feet of those perpendiculars and construct what I'm calling the squared petal family. Okay, so it's this dashed orange family over here. Let's watch it a little bit. Again, its vertices lie at the feet of perpendiculars from F1 onto the petal. So it's a second order petal family. Let's turn off the petal family so we can watch it more closely. Okay, so here's the square petal family. Now I'm reporting up here its perimeter. The first thing you notice is that this family has invariant perimeter. So the squared petal family has invariant perimeter. Does it have invariant area? No, it doesn't. Does it conserve its sum of cosines? Yes, it does. So let's compare the three sums of cosines. I'm going to redraw the first order petals. You can see here that the sum of cosines here for this particular choice of A over B is minus 1.24. This sum of cosine here of the second order petal is minus 0.422, also invariant. And the original sum of cosines of the 5 periodics were minus 1.51. Okay? So it looks like they are decreasing, these sums of cosines are decreasing in magnitude. Very well. Now, I want to make another observation. Let's turn off the petal family and just leave the 5 periodic and this squared petal family over here. Now, I want to actually make another operation. I want to invert the vertices of this 5 periodic with respect to the second focus. Imagine there is a unit circle centered on F2, and I'm going to perform inversions of the 5 vertices with respect to this unit circle centered on F2. What do I get? I get a new family. Let's make this more visible. And I'm calling this family the F2 Inversive Family. Okay, so it's the set of pink polygons. So again, its vertices are inversions of the 5 periodic vertices with respect to F2. It just so happens that this family is inscribed in Pascal's Limaçon, okay? But that's not germane to this video. What I want you guys to notice is that the left dashed orange family, the square petal family, which has constant perimeter, is homothetic to the right-hand side pink family, the F2 inversive family, which also has constant perimeter, and I'm reporting its perimeter over here. Okay, its sides are parallel, and the sum of cosines of both families is identical. I'm reporting them here. You can see that these two numbers, the sum of cosines of the F2 inversive family is minus 0.422, and the sum of cosines of the squared petal family is also minus 4.22. Their two perimeters are identical, but they're not simple multiples of each other because they depend on that radius of inversion that I chose to produce the pink family. Okay, which means that I could have chosen a particular radius of inversion to make this pink family identical to this one. Alright, so it would be something like I would have to scale it down by some ratio here. But then these two families would be perfectly identical, but right now they're just perfect homothetic copies one of the other. Okay, so that's pretty nice. Both invariant perimeter and homothetic. Okay, now let's move on to the next thing. I'm going to turn off this right inversive family here. Okay, I'm going to recenter the diagram over here. And I want to do a very interesting related operation. Instead of inverting the 5 periodic vertices as we just did with respect to F2, I'm going to invert the vertices of the square petal family with respect to F1. So I can actually draw this inversion circle here. So imagine this unit radius circle centered on F1, and I'm going to perform inversions of these 5 orange vertices with respect to the circle. Okay, so what am I going to do? What am I going to get? Invert petal squared. I get a surprise. When I perform this inversion, let me see if I can manage to put this in a reasonable location. Yes, I can. There we go. So when I perform the inversion of these orange vertices with respect to the circle, I get this new dashed blue family, which is rather interesting because it is a perfect homothetic copy of my original family of 5 periodics. Now you can see it's scaled up a little bit, but of course, and I don't have this control here, I could again choose a particular inversion radius to make this dashed blue billiard family be identical to the original 5 periodic family. So these two families are connected by 3 operations. You do the pedal transformation, you get that bicentric family. Then you do a square pedal transformation to get that dashed orange family. And then you take the dashed orange family and you invert it with respect to the focus. And you get this homothetic copy to the elliptic billiard. Now I'm going to show you guys another set of 3 operations that is going to get me the exact same dashed blue family. So let's go ahead and erase them. Okay. I'm going to start by inverting the vertices of this. Recall the first inversion that we did. We actually inverted. We inverted the vertices of the 5 periodic with respect to F2. Okay. Let me invert the vertices of the 5 periodic with respect to F1. Okay. So you see here the two inversive polygons. In fact, the product of their areas is constant if n in my n periodic is an odd number, but that's not germane to this video. You can see that these two inversive polygon families, they are really the same family, but they're sort of out of phase and mirrored about the y-axis. Okay, the product of their areas is constant. But I want to forget about the one on the right, and I just want to focus on this one now. So this is my F1 inversive polygon. I've taken the vertices of my n periodic, and I've inverted them with respect to a circle centered on F1. This family, much like the F2 inversive, has constant perimeter, and it conserves its sum of cosines. Okay? Now I want to take this family, and I want to compute the antipodal polygon of this pink polygon with respect to F1. So how do I do this? Just need to find it here. Inversive polar. That's it. Okay, so imagine running spokes from F1. I believe I have those spokes. Yes, I have those spokes. So imagine running spokes or lines from F1 onto the vertices of my inversive pink polygon, and when these guys meet the vertices, I'm going to draw a perpendicular line here, okay, in such a way that I'm going to compute what I'm calling here the antipodal with respect to F1 of my inversive polygon. So you can see that this antipodal polygon, which we're going to call here also the polar polygon, has sidelines which are perpendicular to the lines connected. The sidelines go to the vertices, but they're perpendicular to the line connecting that particular vertex to this fulcrum point F1. So you get this new family. Again, owing to the special geometry of this confocal pair and this 5-periodic family, it just so happens that this new family, this dashed pink family here, is also bicentric. It's inscribed in a fixed circle, and it circumscribes another circle not shown in this particular picture here. So there's going to be another circle in here, which this family circumscribes. So there's a bicentric, there's a pair of circles, and this family is interscribed between these two pairs. Therefore, it's called a bicentric family. Okay, so this bicentric family was obtained automatically by this operation. I just got the inversive and computed the antipodal with respect to the inversive. Okay, now let's repeat this operation. I'm going to compute now the antipodal to the antipodal. What do I mean by that? Let's turn off these spokes. I'm now going to think of spokes that that are connected between F1 and the vertices of this antipodal, or also known as a polar polygon. Okay, so this polar polygon. Oh, by the way, I forgot to mention, the polar polygon does not have constant perimeter, but it does conserve the sum of cosines. Recall that that other bicentric family had the same properties, okay? So this seems to be a property of bicentric families, that they conserve the sum of cosines, and this is not proven yet. Okay, so I'm going to, going back to what I was saying before, I'm going to compute the antipodal to the antipodal, the square antipodal polygon. So let's do that. How do we do that? The antipodal to the antipodal. I think this is it. Yes. So this new polygon here is the antipodal to the polar, or the squared antipodal of my inversive polygon. So you start with this solid pink polygon. The first order antipodal is this dashed pink, also known as a polar, and the square antipodal is this dashed blue polygon here. Now notice what's going on. This blue polygon is also a perfect homothetic copy of the original 5 periodics. In fact, this is the same polygon that was obtained by the first set of 3 operations. Let's recall them. I started with the 5 periodics. I computed a bicentric pedal family with respect to F1. Then I computed a square pedal family with respect to F1. It's barely visible here. It's this dashed orange family. And then I took this dashed orange family, which was, as we had seen before, homothetic to that right-hand side inversive polygon. So this squared orange, this dashed orange family here of constant perimeter. And I took this family and I inverted it with respect to a unit circle centered on F1. And when I did that, and I actually have that control here, I fall onto the same polygon. Okay, that's why this has become sort of a darker blue, because I'm drawing it twice. So here it is drawn once, here it is drawn twice. You can barely see the second drawing because it's actually on top of it. So I can get to this blue polygon either via the 3 operations involving a pedal, a square pedal, and an inversion, or I can get to the blue polygon via an operation that starts off with an inversion of the 5 periodic with respect to F1, giving me this pink polygon, and then performing the antipodal operation twice, which is going to get me to here. So it's as if we have a complete cycle of 6 operations. Right? You can sort of stay in the cycle by performing these 3 operations followed by 3 operations, and it's just going to be a periodic shuffling of polygon families. Now, as we look at what's on the screen right now, let's try to pick out what's going on. Okay. Oh, by the way, let's actually compare the area of this bicentric dashed pink here with the bicentric solid orange. And I believe I have this somewhere. Let's see if I have that drawn somewhere. So it would be the area of the polar. Okay, I'm gonna have to leave this in the description of the video because I'm not seeing this immediately. So what I want actually is the area of the polar divided or multiplied by the area of the petal. Okay, I may have made a mistake here. It looks like the product is constant. pedal times polar and not the ratio. I would have expected the ratio to be constant, but maybe there's a mistake in the implementation. And I'm gonna report in the description of the video what the correct answer is. But in any case, let's actually recap. We start with this phi periodic. Okay? It has constant perimeter. It has constant perimeter. We add to it a pedal family with respect to F1. This family is bicentric. It doesn't have constant perimeter, it doesn't have constant area, but it does have constant sum of cosines like the blue family. Then we compute the square pedal to this family. We notice that the square pedal has invariant perimeter. We also notice that the square pedal is homothetic to that right-hand side pink family of inversives with respect to F2. Let's turn that off. Then we take this square pedal and we invert it with respect to F1. And we get a family that is homothetic to my elliptic billiard. Of course, I could make these two families be identical simply by regulating the radius of my inversion circle. Right? So the radius of my inversion circle right now is 1. But if I changed it, I would make this dash blue family, I could make this dash blue family be of the exact same size, or the homothetic ratio be equal to 1, in such a way that the two families would just be translated versions of each other. Okay, so I have a sequence of 3 operations that takes the original 5 periodics to a translated version of itself, and it's translated by exactly the focal distance. Alright? So this was path 1, and then we talked about a path 2. I start with my 5 periodics, then I compute the inversion or the inversive polygon. Okay, this pink thing here. It also has invariant perimeter. Then I take this inversive polygon and I compute the antipodal with respect to F1. Then I get a bicentric family, which conserves sum of cosines, but like the original one, it doesn't have, like the former bicentric one, it doesn't have invariant perimeter, nor does it have invariant area, but it does have invariant sum of cosines. And then I compute the antipodal to the antipodal, and I go back to that homothetic family, that phi periodic family, homothetic to my elliptic billiard phi periodics. Does this work for other ends? Can I go to n equals 4? Yes, I can go to n equals 4. I'm going to get the same phenomenon. Can I go to n equals 3? Yes. I'm getting things that are getting a bit more, let's say, eccentric, but I am getting the same phenomenon. Let's see if we can look at everything here in the same image. Yes, so you can see now that I've gotten, I really have to change that radius of inversion so things are on the same scale. But the important thing here is that my dash blue family is homothetic to my original dash blue family. Let's go to n equals 6, and I'm probably going to have to scale this up a bit. So here's my n equals 6 non-self-intersecting, because there's self-intersecting n equals 4, n equals 6, and so forth and so on. But I'm getting the same phenomenon. So it looks like this is a phenomenon that maps an n periodic to a translated version of that n periodic by going through 3 transformations, be them pedal, square pedal, inversion, or inversion, antipodal, square antipodal. And both of these sequences of 3 operations are going to get me from that blue phi periodic to this dash blue phi periodic. Anyway, guys, appreciate your time. I hope not to have been a bit long-winded, although I was, and I'll see you in the next video.